back, everybody. So today, I want to talk a little bit about the algebra of probability distribution functions. So the algebra. So let's first look at discrete distributions. In this case, I mentioned last time that given any series, summation a sub k going from 1 to infinity, which sums up to 1, we can define a probability measure on the natural numbers, a probability measure. P on the natural numbers, such that probability of the number n is just simply a sub n.
So you want all these to be non-negative, right? All the terms to be non-negative.
Yeah, given any series AK is non-negative. Yeah. Well, although one could build a theory of what are called signed measures, we won't discuss that here. But let's just take non-negative things. So an example, I gave some examples of discrete measures last time. Let me give one more example now, called the geometric distribution. And it comes from the geometric series, so geometric distribution. Arises from summation r to the k minus 1, 1 minus r, k going from infinity. This is 0 less than r less than 1. Fix the r. So the probability that of a natural number n is just r to the n minus 1, 1 minus r. So in this case, the probability of n, the probability measure we attach to n, which is simply r to the n minus 1, 1 minus r. As you can see, this is perfectly fine. And I'm going to use this now in order to find a formula for the nth prime. Okay, so this is an interesting idea. But before I do that, let me just point out that given two discrete distributions in this way, given two distributions in this way, so in other words, if I could write probability that i.e. probability x equals n is given by a sub n, taking a random variable x, and the probability that x equals n is now given by a sub n with this property. So given two discrete distributions x and y, probability of y equals n is say b sub n. So I have two series, summation an coming to 1, summing to 1, summation bn summing to 1. Then the question is, what is the distribution for x plus y. So the probability that x plus y equals n, well, x can, is a random variable that only takes on natural numbers. So these both are I plus j, such that I equals n. So this is simply going to be equal to summation a sub I b sub n minus I going from 1 to n. So this is a distribution of the sum. So in this way, it's pretty easy. In the discrete case, the sum of two random variables have the distribution is easily determined. And if I asked you, for example, what is the probability that xy equals n, then you see immediately that this has to take on a sub d, this has to take on b sub n over d. So it's often what's called a Dirichlet convolution. D divides n, a sub d, b sub n over d. So in this way, you reinterpret a familiar object of elementary number theory called the Dirichlet convolution as, in the case of this setting, as describing the probability distribution of the product of two random variables. Now, if I were to ask the same thing in the continuous case, it's not so simple to answer these questions, and we will discuss that in a second. But before I do that, let me point out this application of the geometric distribution to the study of primes. So to motivate a discussion, we'll need to recall the Mobius function. So this is a function, that's why, you see, I was very averse yesterday and earlier to use mu for a measure, because I like mu for a Mobius function. So mu of 1, mu of n equals 1 if n equals 1, minus 1 to the k if n is a product of distinct primes, p1 to pk, pi distinct primes. And 0 otherwise. So this is the definition of this function. I'm sure all of you have seen this before. The fundamental property, if you did not see it, here it is. Fundamental property of this function, basic property, which is also important in sieve theory, is that summation d divides n mu d always equals 1 if n equals 1 and 0 otherwise. So in other words, this is a very convenient way of sifting one from other elements. And the proof of this is just a one-liner. Proof is one line. Since the Mobius function is only supported on square-free numbers, you give me a number n, I need only take the product of the distinct primes. So let capital N be the product of the primes that divide n. Then summation d divides n mu d is the same as summation d divides capital N mu d. And now capital N is a square-free number. Let's say n equals p1 to capital N equals p1 to pk. Then any divisor corresponds to a subset of these primes. And so with a little bit of reflection, you see that this is nothing but minus 1 to the j, k choose j going from 0 to k. Now, of course, if n equals 1, meaning little n equals 1, this was equal to 1 to start with, then there's just one term there, that's mu of 1, but if m at n is not equal to 1, this is 1 minus 1 to the power k, which is 0. So here I'm assuming k is not empty, k is not 0. So if k is not 0. But if k is 0, then it's 1. So this is one line proof, but it's a very powerful fact. And it's very important and useful in mathematics and sieve theory especially. So, so let me use this geometric distribution in conjunction with basic properties of the Mobius function to derive a formula for the nth prime number. And this is certainly not my idea, but it's an idea of M. Gandhi. M is not Mahatma. So, couldn't resist that joke. So the theorem to J.M. Gandhi, 1971, let Q sub n equal the product of the first n primes. Then the n plus first prime equals minus log, the greatest mixture of minus log 2 of summation d divided q sub n mu of d over 2 to the d minus 1 minus a half. This is a very cute formula for the n plus first prime, given the knowledge of the first n primes. And the proof uses the geometric distribution. So observe that summation 1 over 2 to the n going from 1 to infinity is what? 1/2 plus 1/4, so it's 1. Okay? And so by the philosophy of that we were talking about, every time you see a summation adding up to 1, you can develop a distribution. Anytime you see an integral integrating to 1, you can develop, we'll come to that later. But here we have a sum coming to 1, summing up to 1. Therefore, define probability of n to simply be the measure of n to be just simply 1 over 2 to the n for each natural number n. Then let's consider two sets. Let A sub d be the elements, well, let's just put it this way, the collection n such that d divides n. And let A superscript n be the collection m such that m is co-prime to n. These are two subsets of the natural numbers. And so let's try and find out what the probability measure of these sets, what is the measure of these sets? Well, they're easy calculations. We'll leave this fat, so this off. It's clear. Measure of A sub d, which is simply 1 over 2 to the d k going from 1 to infinity. That's a geometric series. 1 measure of this set is just that. Now what about the measure of the A superscript n? Probability A superscript n is equal to the measure of, so we calculate each one. It's just we make sure, so we go over all the m's, we make sure that m and n are co-prime, and use this result, GCD is 1. So keep in mind that we have that. And so we interchange.
1/2 to the power n.
Yeah.
Pardon me? Oh, 1 over 2.
2.
Yeah, 1 over 2 dm. Yeah, thank you. Okay. For that m, we figure out whether it's that. Okay, absolutely. So d divides m, mu d, and here we have 1 over 2 the m, m, d divides m. But this is, we calculated, it's the measure of a sub d. So better to write. Therefore, we get this is simply nothing but a divides n mu d over through the d amount. So the measure of this guy is this. Nice calculation. So now let's see if Q sub n is the product of first n primes, then what do we have? We let's calculate P of a Q sub n, collection of all numbers. So A superscript that is the collection of all numbers which are co-prime to Qn. And it's the totality of that. Well, 1 is certainly there, so it's 1/2. What's the next one? It's the n plus first prime is the next one. And that has measure 1 over 2 to the p sub n plus 1. And then higher terms. Well, p sub n plus 1 probably is not one of the elements because it'll have factor, common factor. But whatever it is, let's just put e sub n for the rest of this stuff. Okay? Whatever e sub n is certainly less than 1 over 2 to the p sub n plus 1 plus 1 plus 1 over 2 to the p sub n plus 1 plus 2 dot dot dot. I'll overkill. I'll add everybody. See what it will be a bunch of numbers, probability of certain numbers which are co-prime to Qn, but I will just throw all this in. Their measures will be smaller, but certainly this is certainly true. And what is this? This is certainly less than 1 over 2 to the Pn plus 1. Right? Less than or equal to, if you like. Right? So En is strictly less than this, for sure. And this sum is at most that. Because it's a geometric series. Do your thing, you get that. Therefore, what do we have? We have so thus we have this probability. On one hand, we have this fact, P of A Q sub n equals 1/2 plus 1 over 2 to the P n plus 1 plus E sub n. On one hand, we have this. On the other hand, we have a formula for this from here, which is given here, which is equal to summation d divides q sub n mu d over 2 to the d minus 1 by that formula. So on one hand, the measure is given by this formula. On the other hand, the measure looks like 1/2 plus this stuff. So therefore, if I look at this quantity and subtract a half from this thing, d over 2 to the d minus 1 minus a half, subtract that half, then this quantity is less than 1 over 2 p to the n plus 1 plus e sub n is also less than 1 over 2 p to the n plus 1. But on the other hand, this quantity is also bigger than 1 over 2 p to the n plus 1. Right, this quantity, I mean, this difference is 1 over 2 p to the n plus stuff. So it's certainly bigger than 1 over 2 p to the n. Okay? And this plus stuff is bounded by 1 over 2 p to the n. Now I multiply through by 2 p to the n plus 1. Like so. And see that this silly thing is between 1 and 2. Therefore, if I take log base 2, taking log base 2, we get, well, 0 is less than Pn plus 1 plus log base 2 of the sum log base 2. Okay, so this implies that minus log base 2 of the stuff, which is put star, is less than Pn plus 1, and it's less than log minus log star plus 1. So I have a number trapped in an interval of length at most 1. Therefore, this number must be the greatest integer. So that finishes. So this means Pn plus 1 is the greatest integer minus log base 2 of that stuff. Very cute application of geometric distribution. Okay, so is it good for anything? Well, I don't know. Remember Turan on lecture number 1? We don't know. Don't judge it. It's an interesting observation. And who knows? It could be. So in the case of discrete distributions, it's pretty simple to calculate the distribution of sum of two discrete distributions and the product. So the product, like a Dirichlet convolution, the sum, like a, what do they call it, a Cauchy convolution. Some Cauchy. Yeah. It's usually is very much similar to the convolution in theory of Fourier transforms, yeah, or Laplace transforms, I guess. So let's now ask a question. What about continuous systems? What can we say if we know the density function fx and fy? What is fx plus y? And what is fxy? And of course, one can also ask what is x over y, things like that. I'll not get into all the detail, but let's just do these for the day. Now, in order to discuss this question, I'll need to review measure theory. Not everybody may have had a course in measure theory, so let me just kind of give you a quick, 10-minute crash course on measure theory. So we talked about it last time. We said you have a measure space, basically the sigma algebra of certain subsets on which the measure function is defined, satisfying the usual properties of measures, additivity, etc. So the first thing that I actually need is what's called Fubini's theorem. So if x mu and y mu are two measure spaces, one can define a product measure lambda, call it, or sometimes people write mu cross nu, on the product space. And the way you do it is you take you take a measurable set A and a measurable set B. A is in X and B is in Y, and then you would say lambda of A cross B is just mu of A times nu of B. You do these for these measurable things, and then generate this thing on the sigma algebra of all of these. So it's pretty clear what to do. So now, if Fubini's theorem says, let f be a measurable function on x cross y, suppose that either one f is non-negative. By the way, in the whole of measure theory, whenever we write things, it's always almost everywhere. You don't have to have it everywhere. Keep that in mind. I'm not going to say it. So when I say this, it's almost everywhere. Either this or the integral of just to rub in, there's a product thing, I'm gonna put double integral. So either the integral, you know, this absolutely is convergent, or it's non-negative, then what you can say is that the integral over x, integral over y, f of x, y, the nu, the mu, this integral is equal to the integral x, sorry, changes around, the integral. So actually this way of writing it, well, let me continue this way first. And then it's equal to the double integral over the total measured product space. So this integral, last integral, is over the product space.
Perhaps the sigma finiteness is.
Yes, make.
Yeah, sigma finiteness we
It's
need.
needed.
Yeah, so I'm just assuming that that's all there. Yeah. Yeah. So here. Yeah, so here we are looking at this double integral with respect to the product measure, and then we can interchange that. So that's basically Fubini's theorem. So one important theorem to learn. The second fact I want to emphasize is the Levitic dominated convergence theorem. So suppose that we have a sequence of functions. It's a sequence of measurable functions. And such that mod fn is less than or equal to g, with g measurable, and suppose that measurable and integrable, yeah. And suppose that fn tends to f. Again, everything's almost everywhere. Then f is integrable, and we have integral fn over my
G
space.
should be integrable.
Pardon me? Yeah, G should be integrable. I forgot to say that there. F is measurable and integrable. Fn tends to f. So you have this, in a sense, basically, you're allowed to take the limit of Fn into. Good. As I said, my goal here is not to give you a course in measure theory, but rather just to review some basic facts that you might need in the course of the discussion. One more thing which is very useful, and it's actually a consequence of this dominated convergence theorem, is differentiation under the integral sign. So suppose that, let me confound R2. Suppose that our space is R2. Suppose that we have an interval A, B, cross CD, say, in R2. And we define g of y to be the integral A to B of f of x y dx. When I write dx, it's d, the Lebesgue measure. So we have this for some measurable function, for some differentiable function actually, for some f differentiable. And suppose that partial df by partial dy is continuously differentiable. And then we can more or less say, I mean, there might be a small technical condition about it being bounded if it's an infinite interval. Then basically what I'd like to say is that g prime of y is nothing but the integral A to B partial df by partial dy xy dx. So in other words, you can move the differentiation under the integral sign. Okay, I just want you to be aware of these facts because I'm going to use them left and right. The usefulness of this last piece, I think the most impressive example I can give you of the usefulness of this last integral, last fact, is to calculate a very special integral in Fourier analysis. The integral that keeps on appearing in most topics in harmonic analysis. That's this integral of the question of evaluate integral 0 to infinity sine x over x dx. So as an exercise, I think, by the way, I was going to write exercises up, but I think I'll just put them down here as they occur. Exercise. Show this integral is not absolutely convergent. Show that this is not absolutely convergent. So it's a very delicate integral and often treated in complex analysis. But you can treat it using this last thing by a very nice trick, which is really worth knowing if you're going to be a professional mathematician. And that is, so instead of considering this, instead consider g of t integral 0 to infinity e to the minus tx sine x over x dx. So dampen this. T is positive. Dampen this by an exponential decay and look at it. And now the integral is absolutely convergent for any fixed t, positive. So there's no problem with that. And it satisfies these conditions. So you can just check sine x over x, as you know, is bounded. And so e to the minus tx satisfies all these conditions. So we can happily differentiate. So differentiate this with respect to t, and it's minus e to the minus tx sine x. Conveniently kills the denominator. And now this is something that we can, everybody in this room can do, is to evaluate this thing by repeated partial integration. So minus, let's see, how do I do this? It's e to the minus, so I'm going to integrate e to the minus tx and differentiate the other one. So integrate e to the minus tx. So x equals 0. Got this sign. X equals 0 and x equals infinity. Minus, so I always get confused with this. So let's move the sign to the other side so that I don't get confused. So minus g prime of t is there, okay, is equal to that. So now I integrate this with respect to this, and we get what? 0 to infinity, minus is a plus, e to the minus tx sine x, cos x rather, over t dx. Fair enough? When you check the integration, check whether I'm doing it correctly. So at x equals infinity, and keeping in mind that t is positive, when x equals infinity, this is 0. And when x equals 0, sine 0 is 0. So this thing disappears. So you get this g minus g prime of t equals integral 0 to infinity. 1 over t comes out here, e to the minus tx cos x dx. And then I will do another integration by parts. So e to the minus tx over minus t again times cos x. X equals 0. X equals infinity. And then plus, minus is plus, yes. 0 to infinity. E to the minus tx over t times minus, cosine derivative is minus sign, so the minus sign here. Fair enough. Hope I did this correctly. By the way, I should have pointed out, the proof of this fact with this differentiation under the integral sign is really an application of the dominated convergence. It's really cute. So the dominated convergence theorem is probably the most important theorem in measure theory. It really simplifies life. You don't have to worry about this and that. So now we have a kind of an integration. So here, let's just calculate these limits. At x equals infinity, this is 0 again. And x equals 0, cos 0 is 1. And x equals 0, that's 1. So what do I get? Pardon me? I get
1 upon t.
1 upon, no, there's a t outside.
T
One
squared.
upon t squared, right. 1 upon t squared. And then,
They have a minus.
No, minus cancel.
yeah, minus cancelled, yeah. And then now here, we have the 1 over t, so it's a minus 1 over t squared times the integral 0 to infinity of e to the minus tx sine x. And we said the integral from 0 to infinity of e to the minus tx sine x dx is minus g prime of t. Fair enough? Okay. So what does this mean? This means that g prime of t, 1, did I do this right?
This second term should be negative.
This should be a minus sign here? Is that right? Because the g of t is this, g prime of t was this, right? And so I have here 1 over t squared times a minus sign, so that's g prime of t. So 1 over t let's see, minus,
CD.
yeah, 1 over t squared times g of g prime of t, so it should be plus.
Okay.
Should be plus?
It should be plus.
Maybe I made a mistake here. Did I do this right? No, it's okay, I think it's okay, right? Okay, so let's just keep going, minus g prime of t, and what do I have? It's, so minus g prime of t comes out, and 1 plus 1 over t squared, is that fair? Looks
T
okay?
square.
Yeah, good. Then, what do we have, which I have the g prime, minus g prime of t, 1 plus t squared equals 1. So that means minus g prime of t equals 1 over 1 plus t squared, and all of you can integrate 1 over 1 plus t squared, arctan t. So minus, so we end up getting, integrate both sides, it's minus g of t equals arctan t plus a constant. Is constant. You know this joke about this professor who goes to a restaurant. This is not a Siddharthi joke, so I won't be arrested for this. He goes into a this mathematician goes into a restaurant and says he wants to prove to his friend that everybody knows mathematics. So he takes the waitress aside and tells her secretly, I'm going to ask you a question. Just say log x, okay? Just whatever I say, just say log x. So the waitress comes to the table and the guy says, what's the integral dx by x? And she says, log x plus a constant. So there's always a constant, you see. Now, at t equals infinity, we can use the dominated convergence theorem to push the limit process inside, and we get g of infinity 0. So g of infinity is 0, so g of infinity equals 0. Therefore, when I plug in t equals infinity, I've got 0 equals arctan infinity, which is pi by 2 plus a constant. And therefore, c has to be minus pi by 2. So this means that g of t is equal to minus arctan t, and c is, so it's minus minus, it's a plus, so it's plus pi by 2. Fair enough? So what did I do? I was confronted with this problem, but I changed the problem and made it harder. And then applied this technique and actually solved it for any t positive. Now we can take the limit as t goes to 0. And you get that the integral is pi by 2. Check any book in harmonic analysis, Fourier analysis. You will find this calculation done using complex analysis. It's not a trivial calculation. But this is pretty straightforward. I mean, of course, I'm using Lebesgue theory, which is important. Yeah? So it simplifies life considerably. We're going to do the same kind of tricks to discuss what happens with probability distributions.
So why is this G continuous at 0?
Yeah.
Well,
That's something.
the fact is that taking limit t goes to, these are, I would put t equal to 1 over n, okay? And then each of these functions is continuous. And then take the limit as inside. That's what I was saying. There might be a little bit of work to be done, but much more or less good. Were you saying something?
Yeah,
Yeah, yeah, yeah. But this is the idea. So if given f and g, let's say in L1 of R, we define the convolution we define this convolution. It's an exercise using Fubini. Fubini implies that f star g is also in L1. Okay, so now I want to apply this to this understanding to say that given two x, y continuous xy random variables with continuous random variables with distributions with cumulative well, let's say density functions fx, fy, we want to find f sub x. Now remember what we discussed yesterday, recall, we had two words with respect to these density functions which were different from the discrete case, and that is the probability, the cumulative distribution versus the density function. So the cumulative distribution was denoted, I believe, fx u, integral minus infinity to u of fx of t dt. This was the idea. And therefore, on one hand, we should think of this by the fundamental theorem of calculus as the derivative of this. So fx prime should be thought of as the derivative. Everything is almost everywhere. We're not, as I told you, I'm not giving a course on measures here. So you have something, this understanding, or if I have an expression minus infinity to u, whatever that thing is that's the density function. So whatever, right? Whatever I'm integrating, if I have the limits in this form. So with that understanding, let's kind of So how do you calculate the density function? Well, basically, the probability that x plus y is less than or equal to u is my, in my notation, the cumulative density distribution function, right? And what is this? Well, it's equal to a double integral x plus y less than or equal to u of the joint distribution. Now here, by the way, maybe I didn't say it. But well, maybe I didn't say it, but these, I'm going to assume that x and y are independent before I continue. I should say that. So now suppose x and density function of x plus y is going to be, you know, it's a function of two variables. So you've got, if I have to check what is fx plus y, let's see. If I'm going to assume that they're independent, what I'm trying to say is that the density function will be a product of the two. So in other words, I'm going to say that this is equal to a double integral fx of u fy of v du dv with the proviso that u plus v is less than or equal to, I used that thing here, x, let's put an x there. I mean, different letter, let's put z there. Okay, so this is less than or equal to z. So, in other words, the random variable x is going to take on the value u, and the probability that it does that is fx of u, and the random variable y takes on the value v, is the probability of this, and we want u plus v to be less than or equal to z. This is the way to understand this particular statement. When we do that, then you can rewrite this. You can go from minus infinity to infinity, but v now has to go from minus infinity to z minus u. So u is the outside integral, so put u. And here I will put fx of v, sorry, fy of v dv times fx of u. Keeping in mind that everything is absolutely convergent, so I can apply Fourier all the time. Is that fair enough? I mean, so all I've done is, I have said to myself, u is going from minus infinity to infinity, and once I fix u, v is going from minus infinity to z minus u. That's the upper limit. Fair enough? Therefore, now, I want to remove this z minus, so what is going on here? The argument here, v, is going from minus infinity to z minus u. So therefore, this is same as minus infinity to infinity, integral minus infinity to z, f sub y of z. So this part here, v is going up to z minus u. So this is going up to, if I subtract v minus u dv, then I'm all set. And so this is just nothing but fx of u du. Everybody see this? So what am I doing? I'm doing from minus infinity to infinity. I'm just saying that this argument v is going from minus infinity to z minus u. So I'm just making a change of variable. So if I make it v minus u, it's going up, v is going up to z. This is an integral up to z. Okay, so I've got that. And now I rewrite this. I changed the order first. Now I can change the order. This becomes minus infinity to z. And inside, it's an integral minus infinity to infinity. F sub y of v minus u, f sub x of u. This is an integral with respect to v. I've changed the thing, so it's an integral actually with respect to u, and then dx, dv. When I change orders of things around, this is what I get, right? So, keeping in mind that the density function and the distribution function are related by this formula, I see that the density function that I'm after is the integrand here. And the integrand is nothing but the convolution, here, the convolution of the two density functions. So this is the algebraic property. When I add two independent random variables, the density function of the sum is the convolution of the two density functions. Nice algebraic structure. So this shows that the density function, this has to be the density function fx plus y of z, of v or whatever, v I suppose, is my notation. It's got whatever the variable of it, let's fx plus y of v. So this is the convolution. So this is the analog of that Cauchy convolution that we had, you know, so in the discrete case, a sub I, b sub n minus I, that analog of that is this. And as you can see, once you move from the discrete world to the continuous world, you have a lot of things to worry about with respect to convergence, and so you need to bring in some non-trivial measure theory and other things. So that's the density function. Now, what about the product of two? In the discrete case, the product density was the Dirichlet convolution of the two things. So is there something that's similar here? And the answer is there is. So what about xy? Well, here, to define the density function here, density function of xy, we need to look at probability xy is less than equal to zero. Now, keep in mind that these are random variables which are real valued, so y could be positive or negative. Therefore, we have to separate this out. Well, y is negative. We don't consider y equals 0, it's a set of measure 0. Y equals 0, yeah. So you have something like this. And so, because these are disjoint things, and by the properties of the additivity of the measure, we have this. So this is a double integral again. uv is less than or equal to z, with v positive, of probability that the random variable capital X takes on the value u is given by fxu. The probability that it takes on the value v is given by fyv, that y takes on that value. So this is du, dv, and v is positive in this range. In the other case, uv is less than or equal to z, v is negative, we'll do the same thing. X of v, fy of v, dv and v. Now in this case, v is positive. So v is going from 0 to infinity, and u is going up to minus infinity to z over v. And then here, in the second integral, v is negative. So if v is negative, u is bigger than z over. So v is going from minus infinity to 0. That's v. And then u, well, v is negative, so when I divide out by v, the inequality changes. So u has to be bigger than z over v. So this means z over v to infinity. So you get this calculation leading to the sum of these two integrals. Now, we'll change the variables here so that you can get rid of the v. So if I put t equal to, let's see, put t equal to yeah, so if I put u equal to t over v, that's the way to do it. Put u equal to t over v, then I see that since u has to go up to z over v, t is now going up to z. I just want to get rid of the v in this thing. The motivation is you want to write it as something independent of the variables you're integrating over, right? So putting that, we get that the first integral is 0 to infinity of integral minus infinity to, well, t is going up to z. And so I put u equal to t over v, so it's fx of t over v, fy v stays the same, du is dt over v, du is dt over v, and then dt. That's the first integral. What about the second one? Second integral, well, it's again the same idea. You put u equals t over v, so by putting the same thing here, this is going from z to infinity, fx of t over v, fy of v, dt over v, dt. Same thing. Now, in this range, v, which is the outer argument here, is going from minus infinity to 0. It's negative. So all of this can be subsumed as an integral from, so yeah, so if I were to make, yeah, so before I do the next line, so I have an integral from z to infinity. If I make it from infinity to z, which I can do, I just need to change the sign. And then I'm going to move the sign to here, making it positive, exactly. So this way I do that. And so this is really, when v is negative, minus v is the absolute value. So in both cases, it's the absolute value. Oh, sorry, this is a integration from minus infinity to infinity, because this is going from 0 to infinity, this is going from minus infinity to 0, and I've got it rigged up in such a way that the inside integral is the same. But now I've put absolute values. Okay, now this is it. We've done essentially the calculation, because
The integral t is different.
Hmm?
The integral t on the first one is from minus infinity to z, and the second is from infinity to z. Then I think
first one is from minus infinity to z, and the second one, did I, infinity to z. Mm. Did I make a mistake somewhere?
If you were putting a minus in,
Hmm?
would it be better?
Ah, yeah, so if I were to that's right, so if I were to, change v to, so this is, inside integral is from infinity to z. So if I were to put, change all the v's to minus v's, would that help?
You might have to rewrote whether that is possible.
Is this integral?
Hmm?
The second integral is okay in that part?
Here?
Yeah, z by v to infinity.
Oh, pardon me, what are you saying? Z by v to this one? Is that correct, you're saying? Is it's z v, u is bigger than z over v, right? From here,
Yeah.
because v is negative. So z over v to infinity.
So u is therefore bounded by z by v.
Because
Oh,
Because
v is
negative.
yeah.
Negative.
U is bigger than z by
Yeah,
v. Yeah, so then I come to here, 0 to infinity minus infinity to, I change that variable so I can get z to the upper part. And I get this, and if you have, the second part is minus infinity to 0, and it'll be, I had z to infinity first and I change the sign. And so I could put absolute value of v there. Yeah, what, so. I think, okay, so what we should do, are you okay? Okay. What we should do is, is keep it like this.
How did he go from z over v to infinity, from there to infinity to z?
I made the change of variable to be u equals t over v,
Yeah.
okay? So when u equals t over v, t is z, isn't it?
Yeah, so it should be z to infinity, right?
They are, since V is negative.
That's right,
Yeah.
that's right, it should be z to, that's why I did that,
Yeah.
okay? But,
Just sign that question.
yeah,
Right. In that case.
So your V is negative, so that upper limit will be minus infinity.
yeah, so this part from here, I've got minus infinity to 0, and then from z to infinity, that thing, okay? And dt over v, this part is fine now, right? But I'm saying that in the case that,
No, V is negative, that's what
V,
he's saying, that.
V is
so that will be
negative,
minus
so
infinity.
that will be z to minus infinity.
Correct.
That's,
Will be z.
your V is
V
negative
is
in the
negative,
second
so
integral.
when,
this should be minus infinity? Oh, because,
V is negative.
v is negative, yeah, thank you, yes, v is negative, you're right, thank you for that, yes. So now that I have this, I can combine both, right?
You can do what you did earlier.
Yeah, now I can do what I did earlier, and realize this as, from minus infinity to infinity of, so now, yes, basically,
So now, so if you're writing it like this, you'll have a minus sign.
with a minus sign, exactly, writing it like this with a minus sign, so it'll be minus infinity to z, and then,
No.
hmm?
Now we have plus.
I have a plus sign, yes, thank you. Yeah, sorry about that. So now I've got something like minus infinity to z, f sub x of t over v, f sub y of v, dt over mod v, dt, correct? Is that okay? Yeah. Now I recognize, so now the point is that the probability of x, y less than or equal to z is equal to this integral. And the question is, so I can now interchange, nothing depends on the variables now. I can apply Fubini's theorem, and I realize that this is equal to minus infinity to z times the integral from minus infinity to infinity, f sub x of t over v, f sub y of v, dv over mod v, dt, by the Fubini business. And so, whatever minus infinity to that integral, whatever is the integrand is the density function. So this has to be the density function. This is the continuous analog of that Dirichlet convolution. So you see, that was very simple in the discrete case. It's just, you just have to, I made a sign errors or something silly like that, but it's actually pretty straightforward. Okay? So that's what we have. Everybody okay with this? Yeah, so now once we have this, let me kind of give you a acute application to evaluate zeta 2. Now, recall that 2 over pi dt over 1 plus t squared, what is it? Is it 0 to infinity? So if I integrate this silly thing, that's arctan t, and arctan t is arctan infinity minus arctan 0. Arctan infinity is pi over 2, so this is going to be 1. So, fancy name, 2 over p dt over 1 plus t squared is called the Cauchy distribution. So, anytime you have an integration of a non-negative function, you have a distribute, you have a density function. You can think of the integrand as a probability density function. this is the new telescope you have to go back to your first year calculus books and keep looking at these things through this telescope. You'll be surprised what you'll find. So now, once you have this, so let's let x, y be two random variables. With the Cauchy distribution to independent, I keep forgetting saying this, independent variables with the Cauchy distribution. Then let's calculate the product distribution. So according to this formula, the product distribution is given by this thing. So, in other words, what is integral minus, okay, before I continue, let me just point out here, the space is from 0 to infinity. So what we will do is we will take it from minus infinity to infinity, and I guess 4, yeah, okay. Is that right? Yes. When I get 2 of those, yes. No, it's 1. Why would you say 4?
So half.
Yeah. Okay, it's 1, right? Yeah, good. So minus infinity, so let's do minus infinity to infinity. So I'm gonna make it from minus infinity to infinity. And I have this density function, 1 over 1 plus t over v squared times 1 over 1 plus v squared times 1 over mod v, right? dv. Yeah. So this becomes. So now, let me revert back to the 0 to infinity business, because this is double the 0 to infinity business, right? I'm going to take it from 0 to infinity, okay? So with this in hand, this becomes twice integral 0 to infinity of dv, v squared plus t squared, 1 plus v squared. So the denominator is v squared plus t squared, 1 plus v squared. And then there's a v squared here in the denominator, there's a v there, there's a v in the numerator.
We should be 1 by pi square.
Hmm? Oh, there's a, yeah, I forgot the pi, 1 by pi squared. So where's 1 by pi squared we should be doing? Does that look right? No? Is that okay? So now we want to calculate this. So I think you guys can see that there's a partial fraction decomposition here. 1 over 1 plus t squared minus 1 over v squared plus t squared turns out to be equal to 1 plus t squared, v squared plus t squared. And the numerator becomes v squared plus t squared minus 1 plus t squared, so it's v squared minus 1. It's a partial fraction business. So therefore, this integral becomes 2 over pi squared, integral 0 to infinity, v is outside, then I have Pardon me?
Your constant fraction is,
Yeah, that should be b square instead of t square.
that t is a v.
Oh, yeah, thank you. This was a v. Thank you. And so this is a v, and so it's a t squared here, right? Is that what you're saying?
Yeah.
Yeah, okay, good, good, yeah, good, thank you. So, the partial fraction, yeah, so it's 0 to infinity of, so I wrote this as, so if I divide out by, 1 over t squared minus 1, I can see that this is equal to 1 over 1 plus b squared minus 1 over b squared plus t squared. And there's a v at the top, v dv. Okay, so this is equal to that. And so 2 over pi squared minus 1, 1 over t squared minus 1, integral 0 to infinity, v dv over 1 plus v squared minus 0 to infinity, v dv over v squared plus t squared.
Yeah, it's not pi square minus one.
Just pi square.
No, pi squared, sorry. Yeah. Right, thank you. So we have this, right, this is bracket. So we see that this is equal to 2 over pi squared, 1 over t squared minus 1, limit n goes to infinity of 0 to n of v dv over 1 plus v squared minus integral 0 to n v dv of v squared plus t squared. And so here, I'm sure you can see that you can, it's a log calculation, log of 1 plus v squared, but then there's a 2v, so there's a 2 floating around that I have to divide out by, so it's a 1 over pi squared.
And you should write then 2v dv.
Hmm? Did I make a mistake again? Let's see. I had a 2 here, right?
Yeah.
And what I'm saying is, I want to write log of 1 plus v squared, 0 to m, minus log of v squared plus t squared, and it'll be a 2v, so it'll be a half. Is that fair enough? So I've got to keep track of what I'm doing. V is this is a v variable, right? V equals 0. Yeah. Does that look right to you? Okay. So there's a, yeah, that's what I was, 2 over pi squared here, and 1 over t squared minus 1. Okay, so I have log of 1 plus n squared at the top here, and v equals 0, it's 0 anyway. Okay, so there's a log of 1 plus n squared here, and what happens here? At v equals 0, it's log of, let's do this. Log of t squared. So plugging in, v equals n, and v equals 0, it's log of t squared. So log of, so the first thing is 1 over pi squared, 1 over t squared minus 1. So here, what comes out is log of 1 plus n squared. Here, there are 2 terms. There will be a log of n squared plus t squared, and then there's a log t squared term. Okay, let's just look at log of 1 plus n squared divided by log of t squared plus n squared. And then minus is a plus, yeah, plus 2 log t. Is that fair enough? So I have to take the limit got the limit here, limit as n goes to infinity. Right? So as limit as n goes to infinity, what happens here? Well, n squared over n squared is 1. Okay? So this goes to 0. So this is 0. So therefore, this goes to 0. Nothing happens there. So the final answer is 2. I think I may have made a mistake. Did I lose a 2 somewhere? It's I squared t squared minus 1. Okay, that's what comes out. That's what comes out, right? So therefore, the density function for, I'm running out of time, but the density function for the product of the two Cauchy distribution random variables is this. And therefore, I think if you just give me 2 minutes, I'll finish the calculation, okay? So it's an interesting thing because this is a density function. I hope the answer comes out right, and I didn't make a constant thing, but you get the idea at least. So if this is the density function, then we know the density function integrated over the whole space is 1. Plus integral minus infinity to infinity. 2 log t. Yeah, this is where I think, did I somewhere along the line restrict my attention maybe to t positive? I should have perhaps done maybe just to t positive. I should have. Did I do that?
Yeah.
I did. Okay, yeah. So we'll just say this 2 log t over pi.
Greater than 1.
No, no, no. I know what you're thinking, but just wait. Okay. There's a square somewhere here. Okay, pi squared then. Yeah. So what you do is you break this up into 2, 0 to 1, and 1 to infinity. Break this integral up into 2 pieces, 0 to 1, and 1 to infinity. And from 1 to infinity, you make a change of variable 1 over t. And you'll find, I'll do this maybe next time, but when you okay, I could do it now. If you give me about 5 minutes, I'll finish this off. Okay. So this comes out to be equal to, I hope I didn't make a mess with the pi squared over 2. So let's see, pi squared over 2 equals integral 0 to 1 log t over t squared minus 1 dt plus 1 to infinity log t over t squared minus 1 dt. Fortunately, this is fine. So in the second integral, put t equal to 1 over s. Then dt equals minus ds over s squared. So what happens? This becomes integral 0 to 1 log t over t squared minus 1 plus 1 to 0 log of 1 over s, 1 over s squared minus 1 times times the minus ds over s squared. Please check my calculations. So what do we get? We get pi squared over 2 equals integral 0 to 1 log t over t squared minus 1. And let's look at these signs here. So minus integral 0 to 1 of minus log s and there's a minus dx over s squared, and then there's a 1 minus s squared over s squared. Is that correct?
There's one minus two.
Where's the minus?
I mean, you had already taken this minus sign outside, so I.
No, I interchanged
Oh, I see.
1 to 0 to 0 to 1. So this guy goes away. This minus sign and this minus sign becomes a plus. Fair enough? And then I get log s over s squared. So I get 2 integral 0 to 1 log t over t squared minus 1. And I'm going to write this as minus 1 minus t squared. Okay.
1 by s squared.
What?
Sorry, okay.
Yeah. You're supposed to correct me, not confuse me.
Yeah, okay. No, the milling transfer thing has to come to this.
Okay, so now, I'm just worried about the signs here, but anyway, let's worry, did I make a sign error on the left-hand side? No, maybe not.
It's 0 to 1, so you're safe, because log is negative.
Yeah, log, yeah, okay, that's good, yeah, you're right, yeah, good. So now, what we have is pi squared over 4 equals minus integral 0 to 1 log t, and then I use the geometric series, t to the 2k, k going from 0 to infinity, dt. Okay. So in other words, I've got minus summation k going from 0 to infinity, integral 0 to 1, t to the 2k, log t, dt. Right, so far so good. And what is this integral be? Integral 0 to 1, t to the 2k, log t. Well, you all know how to do this. Integrate by parts. So we have t to the 2k plus 1 over 2k plus 1 log t between 0 and 1 minus the integral 0 to 1 t to the 2k plus 1 over 2k plus 1 times the derivative of log t dt over t. And when t equals 1, this guy disappears. And when t equals 0, that kills this guy. So the both of these go away. And so now we have minus integral 0 to 1 t to 2k over 2k plus 1 dt, which gives you 1 over 2k plus 1 squared. What do we get? We get that pi squared over 4 is summation 1 over 2k plus 1 squared. Which is the odd guys, but then let's say that 2 essentially with a 2-part removed. So you get pi squared over 6. I know it's not easy proof of pi squared over 6, but it's a probabilistic proof. It's a probabilistic proof based on density functions. The fact that the density function has to integrate to 1. Okay, so that's more or less, I think it's a good place to stop. Sorry I went over time, but I thought it's a good illustration of the algebra of probability distributions to special values.
So here is when k equal to 0, this last line, and you are putting t equal to 0, then will you get a residue there?
When k equals 0,
Yeah.
I've got t log t. T kills it.
Yeah.
T kills it. Log t is very small. Yeah. I'm sure you can convince
Yeah,
yourself.
yeah, yeah.
Any other questions? And of course, there are you know, details have to be filled in, but you have to get the idea. Everybody in this room can fill the details in, but the idea is the important thing. What is the idea? The idea is the algebra of probability distributions. Sufficiently undeveloped, actually. Because probability people, statisticians don't do algebra. They won't look at algebraic structures. But there's a whole algebra to be unraveled here. And so you can go back and check, you know, open up a calculus book, find out what integral integrates to 1. What is the product, you know, of a measure? What is the product distribution? What does it mean? So you have a meaning to the integral, not just the area under the curve, but a kind of a meaning more like this. Of course, the area under the curve is, of course, when you say it's the area under the curve is the probability adds up to 1, but of course, that's always the case.
So this in the second case when you are calculating the probability density function, you have a dV by V over there.
Mm-hmm.
So does that have anything to do with the Har measure on the material?
Yeah, it does. It does. That's the Har. Yeah, that's what's going on. The Har measure on the multiplicative real group. So it's interesting. You wouldn't see that in the if you tried to play it with the Dirichlet convolution, you wouldn't see it. So the elementary number theory business is not going to help you in trying to transport some of these ideas. But at least it gives you, it suggests the problem.
Yes.
But yeah. I mean, in later lectures I'll talk about the zeta function and how to interpret that probabilistically.